All right, let's get started. I figured out how to present PowerPoint on my machine this time, so hopefully it'll work. I just used Dropbox. Okay. Sorry, started a little late. I actually went to the wrong classroom and then had to sprint here. Then I ended up in WP Carey. It was pretty hell. Anyways, we're here, right? Adam ended up at SYN Scanning last time. All right, awesome. Obviously, I'm not Adam. As much as you might all want me to be Adam, as much as I want to be Adam, it's just not meant to be. I'm Yan. I'm here substituting for Adam today and Thursday. I made Adam go to London instead of me for a conference. So this is the payback. So another confirmation. This is where Adam ended up. SYN Scanning.
Yeah.
Okay, perfect. So let's start back up with SYN Scanning, also known as half open scanning. I've never really heard of it. I mean, it is also known as half open scanning, and that makes sense. I've never heard of it referred to as that. Have you seen a TCP connection in Wireshark yet? In all of these classes? Yeah, what's up? Oh, you did. Perfect. Okay.
So sorry. We actually are past this. We're at the SYN-flooding attack.
You're at the SYN-flooding attack.
We did TCP spoofing.
You did all this fingerprinting?
Yeah.
TCP spoofing?
Yeah.
TCP hijacking? Yeah. I see. SYN-flooding. Okay. A different type of attack. Also has to do with SYN packets. With SYN-flooding and with a lot of other denial of service attacks in general, the attacker takes advantage of this concept that for many operations, something that is very easy for the attacker might be just a little bit harder for the victim, right? And so the attacker, in this case, opens a connection to a remote server. All the attacker has to do is send a SYN packet, right? If the attacker isn't planning on actually connecting to the system or doing anything with that, they don't have to actually keep any state. They just send one packet. Whereas the server, if it is trying to actually handle a connection, it has to hold some state and say, oh, I got this SYN packet. I'm going to respond with an ACK, and I'll wait for the, or I'll respond to the SYN ACK, and I'll wait for the ACK, right? In order for the server to be able to connect that initial SYN with the ACK that finishes the handshake, it needs to hold some state. You need to say, okay, I've received this SYN, I'm waiting for the ACK for that. I've received this, I'm waiting for that. I received this, I'm waiting for that. And as the attacker sends more and more SYN packets, the defender runs out of resources to track them, right? Each SYN packet might take a tiny bit of memory to track, but in aggregate, they add up, right? Have any of you tried to flood from your machines and seen how many packets you can send in a second? Let me show you. This used to be all the rage back when, nowadays, flooding on a single machine scale doesn't really do much. There's not much that my machine could do to overwhelm the server just by flooding it with packets. Back in the day, before network cards would actually handle a lot of the load themselves before a lot of this stuff was kind of much more performant and so forth. You could actually slow down a server with a ping flood, right? Have you talked about ICMP in this class yet? It's just another type of packet, type of protocol. TCP, UDP, there are other ones. ICMP is basically just a protocol to off of the off the top of my head, I don't remember what ICMP stands for. Do you remember, Max?
ICMP?
Yeah. Internet connectivity
Management protocol?
something like that. So it's basically to test connectivity, right? So if I ping google.com, of course, who here has done the ping? Yeah. All right, perfect. So if I ping localhost, this pings localhost, I respond. And of course, when you do ping, you send 1 a second. You can also ping flood. Basically, this floods my local machine with pings, and every dot is like 10 pings, and it's deleted when the response is received. So you can see just from that short time, it took me to say something, it was 692,000 packets were transmitted, right? That's a flood. I can also ping flood Google. This isn't very nice, but we're not nice people here. That was much slower, 477. If I remember correctly, the thing, utility rate limits based on how many packets have been responded to or something. But you can just flood packets. No one's stopping you from that. Except for eventually, if the network admins are paying attention, you will get dropped off the network. But that's okay. Anyways, the point is, it's very easy to generate a lot of packets. In the same way I was generating ICMP packets with ping, I could write a very quick program in Python just to generate insane amounts of SYN packets and send them over. If for every SYN packet, the server wastes just 4 bytes of memory, then in a billion packets, I can exhaust 4 gigs, right? Which is quite a lot. And realistically, these early servers, when this attack was relevant, took more than 4 bytes to at some stage for an additional SYN packet. So the basic idea is you send a SYN packet, the server sends the SYN-ACK, and you just move on with your life. And the server is just waiting there, you know, with the messages on red and whatever. So how do you, this was a major problem, right? How do you fix this problem? There are a number of things proposed. One solution was filtering. So you say, okay, we're just gonna sit on the network and say, you know, as like some sort of a monitoring process running on the server, whatever. Say, okay, there's too many SYN packets coming from this host. Block it. But that's annoying, has false positives, potentially has a lot of complexity. You could increase the length of, or you could limit the length of the heap left queues. They say you don't actually accept arbitrary amounts of connections. You only support, you know, 100 half-open connections at a time, and then future connections are just rejected. So this is 1.5, the solution number 1.5, as we get to solution 2. What's the problem with that?
If you were less easy to take down a server and others from accessing.
Yeah, denial of service. So now you've gone from taking down the server like because it runs out of RAM and crashes to taking down the server because it's off the network fundamentally because it's not accepting connections. That's not much better. So you could also say, okay, well then we're just gonna have a really long queue, but it turns out realistically in these sort of things, no matter how long the queue is, the attacker will be able to exhaust it eventually. You could reduce the timeout, after which you will forget about that half-open connection. This has some problems. There are, again, false positive rates. There are legitimate issues that might cause the final act of the handshake to arrive well after that SYN act was sent. And TCP is supposed to support that, so you don't want to do that. You could have a kind of a round, what's it called, a loop instead of a queue, where, you know, if you get a new connection, you drop the oldest connection that's half open that you haven't finished the handshake with at a server. You might get away with that, but then this has similar issues, right? Just if the attacker floods a lot, you will still start dropping network connections. You might limit per source, but as you've seen, it's trivially easy to spoof source addresses. And the final kind of concept that ended up being adopted was SYN cookies. Right? SYN cookies are described in this document along with some other ideas. If you are really passionate about these attacks, you can read this document. Who wants to have a reading in class with this? So you should tell Adam when he gets back. RFC 4987. Tell your friends. So, let's talk about SYN cookies. This is the solution that's typically used. I actually never really verified myself that this is the solution that's used. That's just what everyone says. So you could take a look, but it seems like a good solution. The basic idea is the SYN packet has that sequence number. Right? The sequence number has some amount of bits that you can use, and it used to be that the sequence numbers were, you know, nice and monotonically increasing, and so they roll over. You've seen issues with that and so forth with predictable sequence numbers. But the basic idea is that you use that sequence number as a sort of cookie in your SYN packet, and the cool thing here is that this doesn't require any changes to the protocol. The TCP protocol doesn't say the SYN number has to be blocked. It can deal with pretty much any initial SYN numbers. And so what you do for your first sequence number of your first SYN packet is come up with this scheme where the top 5 bits is your counter. Right, so you have a 5-bit counter. The following 3 bits, some other stuff. And the important thing is the rest of it. It's a keyed hash of your counter. That's the first 5 bits. And the IP addresses and ports of the source and destination. Right, so you have basically a unique identifier in your sequence number that is keyed, so it's not easily reducible, ideally. You still remember keyed hashes and what's it called? HMAX and stuff. Similar sort of concept. And when you create your first sequence number, you set it to this, and suddenly you don't have to hold any state, because you encoded all of your state in a signed way in the SYN sequence number. So when you send back a SYN act, you send your SYN cookie, your sequence number along with it. When you receive the act, you can look at that sequence number and you can say, hey, did I generate this sequence number? And that's very, very easy to do. You basically just kind of, you look at all the information that makes up the sequence number. Let's go back. Sequence cookie, SYN cookie here. Let's take a look at the top 5 bits. That's your T. So now you have your T. You have the source and destination addresses and ports. You make sure that the T is kind of makes sense for the time period where you received it, and then you can basically verify that the SYN cookie that you received was one that you would have sent And then you say, okay, connection established, and you don't have to worry about half open connections or anything. You just don't track them anymore. The ability to send this sort of not cryptographically secure secret, but like some sort of a secret that is then returned back to you, makes it not necessary for you to store state. There's some drawbacks. Excuse me. The sequence number is a little less kind of normally predictable. I'm not actually quite sure why that's a drawback. Definitely not really impactful in the modern internet. The maximum segment size, now you only have 3 bits for it, but that's, you know, also kind of okay. 8 possible values. Realistically, networks aren't so insanely variable that you need, you know, very granular control of that stuff. And then you can't send any data in your initial SYN packet. Otherwise, what you get back from the server, or your SYN ACK, otherwise what you get back from the client will have a SYN that is different, right? That is a little bigger than this one. And that is basically a price you pay for this sort of denial of service protection. Any questions on SYN cookies?
I still don't really understand like how this solves the problem.
Sure. Let's do some board work. I just noticed these nice boards, so we can. We'll go through an attack. And I'll try to get this in a place where it's kind of recorded for you guys. But then you probably can't see it. Hold on. Well, that's not better. Max, do you want to come hold this?
Sure.
Awesome. Maybe that table also moves.
Low enough.
Yeah, brilliant. Who said that? Extra credit. Tell Adam. All right. Good job, Max. Thank you. Okay. Sorry, I thought I was getting notifications from Adam live. Maybe he's watching. Where's the? Okay. So, let's say you're the server. This is a server, and this is your connection state for half-open connections. Brilliant. Okay, your server. This is your queue for half-open connections, and an attacker starts sending you SYN packets, right? S0, S1, S2. For every SYN packet, without the use of SYN cookies, you have to respond as a server with a SYN ACK, right? SA0, SA1, and SA2. And for every SYN ACK, you have to come up with a sequence number that you need to track, because this server is going to, the client, if it is not a malicious client, is going to rely on those SYN values during TCP communication, right? So you need to remember the next packet you send what your old sequence number was. So in fact, for every connection, every network connection that is successfully established, your server or your machine will track the sequence numbers in the kernel and continue to do so for the length of the connection. So whenever you receive this, and then of course wait for that final act, you need to store a sequence number here, right? So this is your local sequence number for connection 0, local sequence number for connection 1, and so forth, right? And do you understand how, you know, if you never receive this, how just getting more and more packets will end up, we're getting more and more SYN packets will end up overflowing this and basically running your system out of resources, right? Cool. So there's nothing you can do about storing some resources once you've accepted a connection, once the connection is live, right? But this is super easy for the attacker to do. It just takes one packet. There is no connection. So if you can avoid having to store the resources, it's better. So if you, instead of having this, you still have your queue, but only for actually established connection. And in the meantime, you have a secret key that you can use to essentially sign, not securely, but pseudo-securely, sign a response, right? Sorry, this is one. In the SYN-ACK and send it back. So when you receive a SYN, instead of actually generating a sequence number and storing it here, you generate a sequence number in a predictable signed way and send it over, right? The kind of signed way in this case is taking the source and destination IP addresses, some number T that is also included in the sequence number, and a key, hashing it in a keyed way that you can verify later. And you just wait for the attacker or the client, maybe they're not an attacker, maybe they're actually a good guy, right? In the case of the attacker will just never send you an ACK and everything is fine. You don't care because you don't have any state that's being wasted. In the case of the actual client, in the case of the actual client, the client will send you a SYN. You send back your SYN-ACK with a session cookie, with a sequence cookie that you don't have to store. And the client will send it back to you in their response. They'll have your sequence number. And then when the response happens, you process that, you validate that A3, the ACK has a valid sequence number, because you can validate it because only you can generate that hash secret. And then, and only then, do you add connection 3 to your queue, or to your internal state. Does that make sense? Any other questions on this? Awesome.
So does the cookie actually place the sequence number?
The cookie is the sequence number. Yeah. That's the beauty of it. It doesn't require any modifications to the protocol. All right. So, oops. Now we can turn this back on. That was fast. All right. So moving on to other TCP attacks. Of course, this isn't the SYN flooding isn't the only attack that was doable. It was just a very easy, low-hanging fruit. So once that was eliminated, attackers moved on to other things. As I mentioned, you still can't really get away with keeping state for actually open connections. There's no magic bullet there. You still have some amount of memory that is taken up by an open connection. Nicer thing is that open connections are a little easier to track, easier to reason about, so you can have other ad hoc measures to deal with that. You talked about why open connections are easier to track than like half open connections, right? With SYN scanning. You talked about how SYN scanning flies under the radar of some intrusion detection systems. So with the same attack conceptually as this SYN packet flooding, you can also check if a port is open, right? You send a SYN packet to a specific port of a server, and then if that server is open, it'll send a SYN ACK. If it is closed, it'll send a reset. Right? Using that, you can figure out which ports are open without having to do the full connection. One advantage of this is that a lot of intrusion detection systems don't count, or now they probably do, but back when this was developed, didn't count that as a full open connection, wouldn't block it. So you could get away with your port scan without triggering any alerts in that scenario. So anyways, so for those reasons, kind of the fully open connections, they're tracked a little more, and you can't really get away from having some amount of memory usage there anyways. So there's not much you can do about that. Even worse is a lot of systems, let's say high performance web servers, might spin off a thread or a process to deal with each incoming connection. So that's quite a lot of memory used. There can be an interesting attack where, I mean, there are actually all sorts of attacks, right? There's but one other thing is when a server sends you some data over TCP, it needs to be ready to resend it in case that packet is lost. TCP is resilient like that, but that means it needs to keep it in memory. And so until you send the ACK, the server has to keep that data in memory. That's another exhaustion attack. There's other ones dealing with fragmentation on the IP level. I think that's a little deeper than what you really need to be familiar with. But that's generally how other ways to kind of exhaust resources of a server as you're attacking it. Not that I'm saying that you should attack servers. All right. So how do you protect a network or protect a server? Who here has used a firewall? Who here has a home router? All right. So if you have a home wireless router, then you have used a firewall, or have at least been, I mean, really everyone, period, has been impacted by firewalls in the modern world. But if you have a home router, then you own a firewall, and you actively use it every day. The firewall basically says, okay, what should be blocked, and what should be allowed, right? What is an attack? Generally speaking, firewalls work on this asynchronous model where everything going into the firewall. Let me actually switch back to here. We'll redeploy this. There we go. Okay, well, how are we doing on time? Okay, I think we're doing okay. Cool. Okay, so firewall. Often this display the network diagrams as like a brick wall that's on fire. And your machine is here. And the scary internet is out here. And the scary internet might attack you, right? And this applies to, of course, your house, but it also applies much more painfully to larger computer networks, right? Your like ASU and so forth. So generally speaking, you want to be very careful with things coming in that you don't expect, right? So if something on the internet is scanning for port whatever to try to exploit the latest vulnerability, you want to make sure that when it connects to you, that unless you are actively trying to expose something to the internet, it's stopped, right? At the same time, you want to make sure that someone sitting inside the firewall isn't super negatively impacted by the presence of the firewall. So generally speaking, you want to allow anything going out unless it just actively looks super weird, and then there's a question of how to detect that. We'll move on to that next. You want to allow it to happily connect out. And then, of course, you want the response to come back to you as well, right? So this is an interesting sort of problem with some implications we'll get into. Basic idea is, how do you create these firewall rules to allow this to happen without making this a huge pain in the butt for everybody? Basically, what ends up happening is, by default, a firewall tends to close all ports nowadays, and this applies to your home wireless router. It also applies to the Windows, whatever they call it nowadays, Windows Defender firewall, where by default either you or an application that is listening on the port has to allow the ports through. And who here has had to forward a port for like a video game or something? Yeah, exactly. And that's what you're doing when you're forwarding a port. You're basically creating a new firewall policy that says on port whatever, this is actually Counter-Strike, let it through, right? And then you allow incoming connections on that port. Oftentimes nowadays, this is done in kind of a automated fashion using a protocol called UPnP. Basic idea there is using UPnP, a system running on your, or a program running on your machine can say, hey, I'm actually trying to play this game and I need this port. It'll talk to your router's firewall and forward that through. That's, of course, on residential connections, connections that are corporate are much less forgiving. But I can tell you, you can still play a lot of games from my industry days. What's up? So then you, so basically when you're doing kind of your traditional home routing, you have one wireless router and it has one IP to the outside world, and it just makes everything behind it look like it's IP. You can really only have one service on one port listening, so you got to choose. An interesting thing, actually. When does this class end? 1:15. All right, let's go on a quick tangent. Did you guys talk about UDP? Yeah. Perfect. So, I'm going to take you back to this firewall example. And here's a question for you. So let's say you're here on one side of the firewall. Someone else is on the other side of the firewall. And this is what the firewall considers internal, right? So this is inside your house. This is someone else. Maybe they're even behind a different firewall. Worst case scenario. And then there's the internet between you. And this is what their firewall considers to be internal. You want to talk to each other. But you don't have a port open on this firewall, and they don't have a port open on that firewall, right? Or maybe they, anyways, we get to the more complex cases later. So you don't have any ports open. So how would you fix this situation with TCP? First, let me tell you how a firewall works, or a masquerading firewall works. This is the case where to the outside world you appear as one IP address. How a masquerading firewall works: when there's someone behind it, let's say two people behind it, talking to the same service outside. So kind of the inverse scenario of what was just asked. So you go through the firewall and you talk to google.com. And this person goes through the firewall, talks to google.com. How does the firewall know when Google responds who to send that packet to? Right? Obviously, multiple people on ASU's network can go to google.com at the same time. So there is an answer.
Isn't there an outgoing port that gives up one of your firewalls that specifically makes a connection with Google.com?
Yep, exactly. So you create when you create a connection, every connection has a source port and a destination port. So you have a source port and you have a destination port, and the destination port is port 80, let's say, and your friend has a source port and a destination port. The destination port is the same, but the source port is not. So when Google responds, they will send a packet back on each connection to that connection's source port, right? Or now the destination ports they're sending to it. The firewall, of course, says, oh, you're going to port S0. I know where port S0 is. Port S0 is person A. If it gets a packet to port S1, it says, oh, I know S1. That's person B. Right? That makes a lot of sense. So how can we apply that scenario to allow communication between person A and person B behind two different firewalls?
One of them has to have at least some known port open. The other didn't work to them.
Let's say there's no ports open. Of course, yes, if a person had a port open that was configured to, siphon traffic to them, then that's nice and simple, right? You just talk to that port, boom. What if that wasn't the case? We can inject essentially a spoofed state into the firewall, right? So this firewall, when these connections are made, it says, oh, okay, S0 is talking to D0 port-wise. So inside here, there is some sort of a status that says, okay, A opened up connection from S0 to D0, B opened up connection from S1 to D1, and so forth. And this is the table that is queried when Google.com responds. But you remember UDP, right? What's the difference between UDP and TCP? So that's like, let's say that's a drawback. What's an advantage? Or,
Faster speed.
I'm sorry?
Faster speed.
Faster speed. Why is there faster speed?
You're using less bandwidth to take receiving communication.
There's no checks. So you can just start sending any crap you want over UDP. And it should work, right? Because that's UDP. UDP is supposed to work like that. So if I'm A, and I'm talking to, what's another hit website? Reddit? If I'm talking to Reddit, I might send a UDP packet. I mean, Reddit doesn't talk UDP, so this is a stupid example. But other than that, I can send a UDP packet, just like I send a TCP packet. So, okay, instead of Reddit, let's talk about games. Those use a lot. Or VoIP, or something like that. So let's say Skype. This isn't very hip. What's the hip version of Skype? What?
Discord.
Oh my God. Don't tell anyone. Oh, it's discord.gt, right? Or something?
Actually, .com.
All right, we'll at least look presentable. Okay, you want to talk to the chat for gamers. So you send a UDP packet from S0, or let's say S2, to D1, 2, right? And here, the awesome thing is, as far as UDP is concerned, there's no connection handshake. You just start sending data, right? You send a datagram. The server might or might not respond with a datagram. You have no way of knowing. You have no way of knowing if the server is even listening on that connection, right? But in order to be a good firewall, because above all else, firewalls and routers, they need to be able to, not screw up your traffic. Your connection needs to be usable. This masquerading firewall has no choice but to log that connection over UDP as having as being active, right? Maybe there's a timeout, but it has to log it. So it says, okay, S2 to D2 goes to person A, and person B can do the same thing, of course, right? They can say, okay, S3 to D2, D3 over UDP goes to person B. And again, the server doesn't have to respond. The server doesn't even have to have a connection open, but there's no way to really check. So how would you use that to enable communication across two firewalls between two people?
Well, if I send a UDP packet through their firewalls to a known port that's agreed upon between the two clients, and once those ports are open, then the two clients can be communicating.
So the first part is absolutely correct. The TCP part is not. UDP and TCP are two different worlds. So I drew two different squares. I should have been more specific. The connection also has its protocol. So you can have the same connection between the same ports on a different protocol. The firewall will see it as two different connections. But you're right. All that A and B have to do is agree on a port, port X, and A sends a packet from port X to port X. And honestly, this can be two different numbers, from X to Y, and then mirror it on the other side. But let's just keep it easy. From X to X, send it to this other person's firewall, and the other person's firewall says, what the hell is this? I have no knowledge of it. But this firewall says, okay, we'll record that A is talking from port X to B port X, right? And then person B, like you said, does the same thing in reverse. Person B says, hey, okay, let's make a connection from port X to port X, and person B's router says the same thing. There's person B is making connection from X to person A, port X, and all of a sudden, you have created a bidirectional connection with the agreement of both firewalls, even though there were no ports open. So you've punched the port X through the firewall between A and B. And now you can communicate directly. Skype used to use this. I think nowadays Skype might just be a centralized system, but I'm not positive. Don't quote me on that. Could still be this style peer-to-peer. A lot of file sharing platforms use this. Games don't tend to use it. It's considered fairly impolite. But using this, you can create a UDP packet, or UDP connection, as much as a UDP connection exists between two devices very easily. Pretty cool, huh?
This is still pretty detectable by like IDSs and stuff. Like you can be like, oh, that port open. Okay.
Yeah, for sure. This is, especially like this pattern. I guess if you're careful about it, you could just make it look like any other UDP communication, right? If you don't choose the same source and destination port, and if you, oftentimes to make this work, the two parties just flood each other with UDP connections until the states line up in the firewalls. If you don't do that, it's less detectable. But that's typically done. I'm not actually sure why that's done. On paper, it doesn't seem like it'd be necessary, but presumably there's some timeouts and so forth that happen. Other questions on this? Cool. Good insight. That was like immediate attack development. All right. Moving on from firewalls is intrusion detection systems, right? So an intrusion detection system will monitor all communication on the network, or some large amount of communication on the network, and try to say, oh shit, we're being hacked, right? The question with intrusion detection systems is how to specify what being hacked looks like, right? We just talked about, some questionable UDP traffic being flooded from one port to the same port might be a questionable thing that might raise an alert for some human network analyst to look at later. But there could be other ways to detect attacks. For example, you might look at all TCP connections coming into your web server and try to match what is called a signature for an exploit. So typically an exploit has some sort of a detectable, a vulnerability has, to exploit a vulnerability, you have to send it specially crafted data to trigger the vulnerability in a service. And you can, of course, have an IDS that looks at all data that comes across and says, this looks like the type of data that we have seen triggering this vulnerability in other analyses. So that's an attack. An intrusion detection system detects attacks and raises an alert. It doesn't actually stop the attack. An intrusion prevention system will actually stop the attack if it detects it. These are more complex generally. You might have an intrusion detection system that runs on the server and actually looks at all of the data that's received before the server can process it, whereas an intrusion detection system might just simply sit on a network. So, yeah, absolutely. So you put on for a honeypot, you put up a server on your network that shouldn't ever be connected to, and then you see, oh, someone's connecting to this server. This is either a very curious employee or an attacker that is scanning our network. Right? Yeah. So that's a good example of an intrusion detection system that's non-traditional. Traditional ones just will monitor traffic and say, oh, the traffic looks weird. They're more active things like the honeypots. And then there are more heavyweight things like intrusion prevention systems. Interestingly, there is this new class of systems that have come out, have gotten very popular, let's say, in the last 8-9 years now. So that actually sounds pretty silly saying it's new. But it's called a reverse firewall. Traditionally, I mentioned the firewall is mostly concerned with what's coming in. A reverse firewall is actually more concerned about what's coming out. The idea behind a reverse firewall is you're going to get hacked. Right? An organization the size of ASU, for example, and ASU is the size of a large company, is just you're going to have compromises. There's zero way to prevent it. If the NSA has compromises, you're going to have compromises. As in security compromises where hackers get on your network and are able to operate. But what you need to prevent from happening is those hackers begin to exfiltrate the data. Right? So you do your best trying to keep the hackers out. You assume eventually the hackers will get in. And then you have a firewall that says, okay, but once they're in here, they're not getting out, not getting back out. They and there's various techniques that you can use for that. A lot of, for example, botnet infections actually have known command and control servers, so you can prevent communication out to the command and control servers. You can prevent communications out to popular data exfiltration sites, all of this sort of stuff. That's a very active area of at least entrepreneurialism. There's a lot of companies in this space, a lot of money being spent. Whereas intrusion detection systems, traditional ones, have kind of had their heyday back in the 90s, early 2000s, and have mostly been standardized into boringness, let's say. Although with the rise of AI, now you can say, it's an intrusion detection system, but it uses artificial intelligence. People will still pay a lot of money. All right, where is networking research nowadays? I think these slides are probably about 5 years old, from when Adam first built them, but a lot of research actually is happening in software-defined networks. So everything you've learned about networking so far, at least in this course, really assumes that you have a physical switch that someone sat down, plugged cables in, configured, and then there's this worldwide network of physical switches that are all hard-coded to be plugged into each other. This is less and less the case as software-defined networking rises up. The first kind of cracks in that perception was the rise of the cloud, right? So once you could boot up virtual machines on Amazon AWS and later Microsoft Azure and Google Compute Engine and all Rackspace's offering and whatever. And you could also create virtual networks to connect these computers. People started thinking, do we need to have these very strict network policies where the switches are physically plugged into specific other switches? And all of this is designed ahead of time and, overseen by kind of like grumpy old men with big beards and from the that had learned networking in the 1980s. And people have been making moves to change that, right? To, for example, come up with an architecture where maybe instead you still have your switches, but they're all plugged into every other switch. And in software, you define how all of the routing works and what switches they actually communicate. And this introduces an interesting new attack surface, which is the controller of that software-defined network. They're called SDN controllers. That's another machine that is actually making these decisions, talking to the switches and updating dynamically routing rules and access control rules and so forth. That's a new area of research that, for example, we're pursuing in our lab as well. Actually, Adam is in London, along with one of our students, to present a, wait, no, that's a lie. Last year in Toronto, we presented a paper about software-defined networking attacks, and we're working on some follow-ups to that right now. Firewalls, we're still seeing research into firewalls and intrusion detection systems. As I mentioned, big data and machine learning has started making its way into this field as well. And the idea is that you can, if you need big data, firewalls and network traffic stuff, that's very big data. Maybe you can use that to identify attacks and so forth. HoneyNet, for example, and honeypots and honey controllers and B products of all types are big research areas in networking research. IPv6, who here has heard that we're running out of IPv4 addresses? And we're going to run out, and we'll be killing each other in the streets over IP addresses. I've been hearing this for 20, I'm not making this up, for 20 years. Let's say 19 years, ever since I built my first server. I'm sure it'll happen. I'm sure it has been happening and just like being resolved and so forth. But eventually we'll all be running IPv6, which will do away with the nice, blah, 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 IP address system that we're used to and all familiar with, and introduce an absolute freaking monstrosity of hexadecimal numbers and colons. IPv6 isn't terrible, but it's definitely a little painful to get adjusted to. Has Adam talked to you about DEF CON? Yeah, so one DEF CON, I think it was 2012, maybe 2011. We spent all summer preparing, literally all summer. We had an absolutely insane analysis system that would redirect all traffic to this like insane instrumented machine that would, basically we were unbeatable. We were so ready, our automation was so incredible. We showed up, and instead of IPv4, it's IPv6. And nothing worked. It was so disheartening. A friend of mine quit grad school over that. So IPv6 can be painful if you don't prepare for it. Get ready for IPv6. And then IPsec, but more generally, ways to secure communications on the internet. You talked about crypto, of course. IPsec with this idea that what if we have encryption on the IP layer, right? So when you reach out to a server, you immediately, all communications with that server would then be encrypted. This turned out to be a huge pain in the ass because of many reasons, right? Basically fragmentation and different solutions on the layer right on top of the IP layer is kind of a pain. You can imagine if every major company that sold a networking appliance had their own version of TCP, right? This doesn't exist, but this is what's happening with IPsec. Instead of the true promise of IPsec, where you say, okay, that IP, all communication will be secure, we instead have VPNs. Who here has used a VPN? Yeah, VPNs basically create a virtual network device on your computer. All traffic to that virtual network device gets routed through a UDP or TCP connection over normal IP space to a server and then out from there. For now, that's the actual reality of securing network connections. And who knows what's next? There's a lot of, if I were to remake the slide today, a lot of this 5G, next generation wireless networking stuff. 5G heavily uses software-defined networks. For example, there's a lot of very interesting security properties and there's networking properties with slicing pieces of networks across the world. So your phone could be on the same network IP-wise than it is when you're at home, even though you're across the world and so forth. It's an interesting security space. And a lot of new low power devices. So since, let's say 5 years ago, Bluetooth low power has gotten super big. Everything is like this Bluetooth low power thingy. You're talking over that with your scooters that you rent and so forth. It's a big area that's also has a lot of network relevance. Basically, Bluetooth is essentially also a networking protocol on top of connecting your headset. Any questions about networking? No, it's perfectly clear. Who's excited about networking? There we go. 3 people. That's good. No, it is good. I don't know. I feel networking, people don't get a lot of exposure to networking nowadays. When I was learning about computers, that was like all the rage. Everyone had like TCP/IP on their resume. And like literally skill, colon, like gardening, comma, karate, comma, TCP/IP. So you can also put that down. But karate classes are probably next semester.
Why do you think they don't make it networking class required? Is it like cryptography? It already works.
Yeah, if I had to guess, that's why. Even when I was an undergrad, I didn't have a networking class requirement. Yeah, I think it just started working so normally that it's just normalized. I mean, also back in the day, if you wanted to create a large distributed system, you had to really know TCP and you had to make decisions, right? You know, make this server listen on TCP or UDP, you have to understand the implication. Nowadays, everything is HTTP. So if you're even moved beyond that, no one even learns what the HTTP protocol is. Everyone just uses REST APIs, right, in all of their services. You can get away without ever making a TCP connection to a database. You spin up a cloud database in AWS and you talk with it over REST. I'm not saying that's a bad thing. I think it's actually a very nice step. And whenever I make anything that's distributed, it's all over TCP. But it's very different. So yeah, I don't know. Do we have like a web application development course where we have REST API and so forth?
It's like distributed software class.
Yeah, exactly. So that's where things are moving toward from like core networking. I think this stuff is still very cool, but it's very cool in a kind of a hacker way, not always extremely, you know, applicable in your daily life way. Although honestly, I mean, the amount of time, even recently, where I've had to debug my network in a coffee shop or at on a plane specifically. In a coffee shop, I just tether if things don't work, but on a plane, those networks go down frequently, but often for stupid reasons, like the DNS server died. And so you can still get internet if you put some effort into it. Cool. Okay. It's 1:11, so I'll let you go 4 minutes early. Next class, we're gonna dive into application security. So this is where things get super in-depth. We're gonna talk about assembly. We're gonna talk about processes. It's gonna be pretty exciting. What? I have no idea. Matt's gonna do it. No one has any idea. Just figure it out.